Okay, let's move on with our um, thoughts about electronegativity. We have begun that on the last class, and we defined electronegativity as the ability of an atom to attract electrons within a chemical bond. And now we are applying electronegativity to explain the nature of the of bonding. And we first applied this to the bonding within elements, and we saw that, well, when two atoms have low electronegativity, then they tend to form a metal. Okay. When the atoms have high electronegativity, then they tend to form molecules and covalent bonds. And if they have intermediate electronegativity, then they tend to form a metalloid with a chemical bonding in between covalent bonding and metallic bonding. So now finally, let us extend these considerations to compounds, and that can be nicely illustrated by Ketelaar's triangle, which you see depicted here. So Ketelaar's triangle is embedded in a diagram which has two axes. So the first one is this one here, the x-axis, which gives you the absolute electronegativity of the compound. So this is nothing else but the electronegativity of the atom A plus the electronegativity of the atom B over 2. So it's kind of an average electronegativity. So now on the y-axis, you see the electronegativity difference between the atoms. So now for elements, the electronegativity difference between the atoms is always 0 because we combine atoms of exactly the same type. Therefore, all the elements are actually located here on that x-axis. Okay, you find the cesium to the very left because the cesium has the lowest electronegativity possible. And you find the fluorine here to the very right because the fluorine has the highest electronegativity possible, and all the elements you find here in between on that line. Okay, so that line defines one edge of the overall triangle. So now how are the other two edges created? The other two edges are created by the compound which has the highest electronegativity difference. Okay, because when we go here in the y direction, then we increase the electronegativity difference. And cesium fluoride that you see here is the compound with the highest electronegativity difference because cesium has the lowest electronegativity and fluorine has the highest electronegativity. Okay, so the absolute electronegativity of the cesium fluoride, which is just the average of the electronegativity of the cesium, and the fluorine is somewhat intermediate. Okay, now that defines the position here of the cesium fluoride in that diagram. Okay, so all other compounds, okay, must naturally lie within the triangle formed by cesium fluoride, cesium, and fluorine, or be on the triangle. Okay, so you see here now on the second edge of that triangle, you have only cesium compounds. And here on this edge of the triangle, you have only fluorine compounds. And the polarity within these cesium compounds increases as you actually go from this corner here to this corner. Okay, so that tells you something about the bonding. Okay, as we go here from this corner, we go to this corner, we go from metallic, completely metallic bonding to something in between metallic and ionic bonding to ionic bonding. Okay, so the cesium fluoride would be also the compound with the most ionic bonding character. Okay, now here on this edge, we go from the most covalent situation, fluorine, to the most ionic situation with the cesium fluoride. Okay, The ionicity would increase, for instance, from F2 to OF2 to NF3 to CF4 to HFBF3, BEF2, lithium fluoride to cesium fluoride. So now all other compounds must lie within this triangle here. And the position in this triangle defines what is the percentage of ionic character, metallic character, and covalent character in the bonding respectively. Okay? So lithium oxide, for instance, is located fairly close to cesium fluoride. So we would say that it's quite ionic, but it has also some other contribution from metallicity and covalency. So for instance, lithium hydride is in between a metallic and an ionic bonding situation. It has contributions from both of these. It's fairly far away from this corner, so it has little covalent contribution. So here, for instance, the nitrogen monoxide lies fairly close to the fluorine, so the character is primarily covalent, but not entirely so. The covalent bond is somewhat polar. And well, we could also even attribute small but existing contributions from metallicity. Okay. So from that, you can also see that the nature of chemical bonding is having always contributions from all the three bonding types. They only vary by degree. Okay. We can again also not make a completely entirely ionic bonding situation just because the electronegativity difference is always finite. It can never become infinite. So even cesium fluoride is not entirely ionic, but it's also some covalent and even metallic contributions, just that they are the smallest for all the possible compounds known. All right, so this was the last point I want to discuss within chapter 1 about atomic structure, which is now finished. And from now on, we will move over to the next chapter, which is about symmetry in chemistry. So we have our exam next Wednesday. Okay, so this class will be the last class that will count towards the exam. But because we start a new chapter now, only the part about electronegativity will count toward the first exam. Everything which I teach now in symmetry will be tested in later exams. So let us talk about symmetry in the most general terms. So symmetry is, strictly spoken, a mathematical concept, but it has extremely many applications in chemistry, so therefore it's also very important for chemists. So what can it do, for example, in chemistry? It can be used to classify structures of molecules and also extended solids in crystals. It helps us enormously to understand chemical bonding. In particular, it can be applied to molecular orbital theory, and we will do this in the chapter following the chapter on symmetry. It can help us to predict vibrational spectra of molecules. It can also help to determine optical activity of substances. So these are just a few examples. So in this course, we'll mostly focus on the first two aspects here, the classification of structures and molecules with symmetry and the understanding of chemical bonding with the help of symmetry. Okay, so now how can we define symmetry? What is symmetry? So symmetry is a very familiar concept, but it's not always easy to find a common concept which is omnipresent scientifically. So one way to define symmetry scientifically is to say that symmetry is, this has to do with the self-similarity of an object. Okay, so you see, for instance, a butterfly. You see that the left wing of the butterfly must be self-similar to the right wing of the butterfly. The shape of the left wing has something to do with the shape of the right wing. If the left wing was very different in comparison to the right wing, our butterfly would not look very symmetric anymore. So this is intuitively understandable. So now how can we quantify the degree of symmetry that we have in an object? Okay, so we can do this with so-called symmetry operations and symmetry elements. So now what is a symmetry operation? It's the movement of an object into an equivalent and indistinguishable orientation. Okay. Now, what is a symmetry element? Well, that is either a point, a line, or a plane about which the symmetry operation is carried out. So, for instance, here within the butterfly, we have a so-called mirror plane, okay, which bisects this butterfly here into two parts. And then if we carry out the symmetry operation associated with the mirror plane, then we just mirror the left part of the butterfly to the right side and the right part of the butterfly to the left side. So in the following, let us go systematically through all the possible symmetry operations and all the possible symmetry elements that can exist in an object. So first of all, there is the identity operation. So the identity operation is kind of trivial. It just says that if we do nothing to the object, then the object will be indistinguishable to its original form. Okay, so this is kind of trivial, but the identity operation exists. The identity operation exists in any object. So the identity operation is abbreviated by a formalism. It's called the Schoenflies formalism, named after the person who invented it, with a capital letter E. And all the following symmetry operations that we will get to know also have Schoenflies symbols that characterize the respective symmetry operation. Okay, now what other symmetry operations do we know? So the first one is the so-called proper rotation operation. So this is a counterclockwise rotation about a proper axis indicated by a symbol capital letter C subscript N by an angle of 360 degrees divided by N. So N defines the so-called order of the axis, and N also defines, well, by how many degrees do we have to rotate the object. So for instance, if N is equal to 2, the order of the axis is 2, and we rotate around 180 degrees. If N is equal to 4, then the order of the axis is 4, and we rotate around 90 degrees. So now the proper rotation operation has a number of properties that are worthwhile to consider. So the proper axis is indicated by the symbol C subscript N. And now the number of times we rotate, we apply this symmetry operation to this axis is indicated by a subscript letter M. Okay, so overall a symmetry operation C and M is equal to 360 degrees, okay, over N times M. Okay, so that defines a symmetry operation associated with a proper rotational axis. So now a proper rotational axis has the property that when m is equal to n, then we produce the identity, and it is as though we had done nothing to this object. Okay, so for instance, when n is equal to 2, then rotating 2 times by 180 degrees gives 360 degrees. Okay, and rotating around 360 degrees is the same as not rotating at all, and that's the same as the identity. So if we rotate n plus 1 times, then that's again the same as just rotating 1 time. So for instance, if we rotate 3 times, okay, then that's the same as though we would rotate only 1 time. If you rotate it 4 times, then that would be, if you rotate it 5 times, then that would be the same as rotating only 1 time as well, assuming again that we are talking about an axis that has n equal to 2 as the order 2. Okay, now the highest order rotational axis is called the principal axis. Okay, so an object can also contain more than just one axis. So now if more than one non-conjugate axes of the same order are present, then they are distinguished by primes. The more bonds an axis contains, the less many primes it gets. Okay, so we will learn about when a symmetry operation is conjugate and when it is not in more detail later, but generally you can say that when two symmetry elements perform an equivalent job and equivalent or similar symmetry operation, then they are conjugate, and if they don't, then they are not conjugate. So here's an example that shall illustrate what this exactly means. So you see here a square planar molecule, which is the hexachloroplatinate anion. So the platinum is in the center, and here in the periphery we have the 4 chloro atoms. So the C4 axis is we have here C4 axis, which is the principal axis. So the principal axis stands perpendicular to the planar molecule and goes to the center of the platinum atom. Now, in addition to that, we have a C2 axis that stands in the same position as the C4 axis. Okay, that is because when we rotate 2 times by 90 degrees, then that's the same as rotating around 180 degrees. That explains the presence of the additional C2 axis. So now we have even more C2 axes. We have actually C2 axes that go through the bonds of the molecule. Okay, you see these two here. But in addition to that, we have also C2 axes that bisect the angle between 2 chloro atoms and the platinum atoms. Okay. Now, the 2 C2 axes that go through the bonds, they are conjugate. They perform an equivalent conjugate symmetry operation. And those that do not contain the bonds are also conjugate. Okay? So now the we have to assign primes to axes that are conjugate. Okay, so this C2 here is parallel to the C4, so which is the principal axis, so it doesn't get any prime. Okay, so these two C2s that contain the bonds, they get both one prime, and the other two C2s here, which are conjugate to each other, they get 2 primes because they contain less many bonds than these two. So now we have learned about the proper rotation operation. Let us now consider. We have learned about the proper rotational axes, which are C4, C2. Then we have 2 C2 primes and 2 C2 primes. Okay. So now let us see how many symmetry operations we have associated with these axes. And you see the symmetry operations here. Now, in order to determine the symmetry operations, we need to see how many independent and unique symmetry operations can we carry out with each symmetry element. So we can look at the C4 symmetry operation first, for instance. So for the C4 symmetry operation, we have to consider all operations between C4.1 and C4.4. After C4.4, we have produced the identity. So we do not have to really consider the C4.4 because it can be expressed by the more simple symmetry operation of the identity. But what about the C4.1, the C4.2, and the C4.3? So the C4.2 is actually the same as the C2.1. Okay, which is associated with the C2 symmetry element here. So again, rotating 2 times around the C4 axis is the same as rotating only 1 time around this C2 axis, and therefore the C4.2 is already expressed by the more simple symmetry operation of the C2.1. Therefore, we do not count the C4.2. Okay? So that leaves the C4.1 and the C4.3, and these two are actually really unique symmetry operations that cannot be expressed by any other more simple symmetry operation. Okay, now we can go next to the C2 axis here. So principally, we have to consider the C2.1 and the C2.2, but the C2.2 is the same as the identity. So therefore, we only consider the C2.1. Okay, so the C2.1 is here. So now we still have the other C2 primes and the other 2 C2 primes to consider. So now for each of these, we only consider the C2.1 symmetry operations, but not the C2.2, because the C2.2 symmetry operation is already expressed by the identity. So we have only 2 C2.1 prime symmetry operations, and in addition to that, we have 2 C2.1 prime symmetry operations. Okay, now we have fully discussed the proper rotation operation. So let us move from the proper rotation operation to reflection operations. So reflection operations are denoted by the Schoenflies symbol sigma. So the reflection operation is carried out around a mirror plane, which is also called a reflection plane. Okay, so now we are not carrying out our symmetry operation of a line around a line anymore, as we did for the rotation, we carry out our symmetry operation around a plane. So there are two different kinds of planes. There can be vertical mirror planes. They are denoted sigma subscript 3, and horizontal mirror planes that are denoted sigma subscript h. So what's the difference? So a horizontal mirror plane stands perpendicular to the principal axis. A vertical mirror plane contains the principal axis. So this is illustrated here for the example of the BH3 molecule, which is a trigonal planar molecule. So the principal axis of the BH3 molecule is a C3 axis standing here. And we have here a horizontal mirror plane that stands perpendicular to this C3 principal axis. So note that when we carry out the symmetry operation associated with this mirror plane, reflecting at that mirror plane, then none of the atoms move. Okay, the boron stays at its position, the hydrogen atoms also stay at their position. So nonetheless, the symmetry element and also the symmetry operation is present because points within the object, points within the atoms still move. Okay, so carrying out that symmetry operation would move, for instance, the top half of this hydrogen atom here below the mirror plane, and the bottom half of this hydrogen atom would be moved, well, above the mirror plane, and that would apply to all the atoms within the object. So still points within the object are being moved, and that's the deciding criterion, not necessarily the entire atom has to move in order to have a symmetry operation present. So now, in contrast to the horizontal mirror plane, we have the vertical mirror planes that now contain the C3 axis. Okay, and you see the three vertical mirror planes here, and all of them contain the C3 axis. So each of these mirror planes contains boron hydrogen bond. So the first one contains this boron hydrogen bond, the second one contains this boron hydrogen bond, and the third one contains this boron hydrogen bond. Okay, so these mirror planes really move atoms within the object, however, not all of them. So for instance, for this one here, we are swapping up the positions of these atoms, but the boron stays at its position and the hydrogen its position. And for the other two, there are analogous transformations. Okay, so how many operations do we have associated with a mirror plane? So there's only one reflection operation associated with each mirror plane, because when we reflect 2 times, we produce the identity. Or in more general, when we reflect an even number of times, we produce the identity. So for instance, if we reflect 4 times, we produce the identity, 6 times, we produce the identity, and so on. So when n is odd, then it's always the same as carrying out the symmetry operation only 1 time. So for instance, if n is equal to 3, it's the same as a sigma 1. When n is equal to 5, it's also the same of a sigma 1, and so on. Okay, so now There can also be mirror planes, vertical mirror planes in objects that are conjugate, and which are not conjugate. And when they are not conjugate, then we have to distinguish them by primes, and the number of primes depends on how many bonds the mirror plane contains. So here's an example. Here's a water molecule. It contains two vertical mirror planes. Okay, so the principal axis, the C2 axis, stands here, and we have one vertical mirror plane which is within the plane of the molecule, and we have another vertical mirror plane that bisects the molecule. So now, obviously, these are not conjugate. They perform different jobs. That can be, for instance, seen by the fact that this mirror plane here does not move the atoms at all, okay, while this mirror plane here swaps up the two hydrogen atoms. Okay, so certainly they are not conjugate, so we must distinguish them by primes. So now this one here contains the two bonds, while this one here doesn't contain any bonds. So therefore, this one here gets the higher number of primes, this one gets 0 primes, and this one here gets 1 prime. Okay, then there's a special type of a vertical mirror plane, that's a so-called dihedral mirror plane, which is denoted sigma subscript D. So we have a dihedral mirror plane when we bisect, when these mirror planes bisect the angle between twofold axes. That means axes that have the order 2. So an example is shown here. Okay, so this is again our hexachloroplatinate anion, which is square planar. So we have here these C2 axes that goes to the bonds. Now you see we have here two mirror planes that are vertical mirror planes because they contain the C4 axis, which is the principal axis and which stands here. And these two vertical mirror planes, they bisect the angle between the two C2 axes. For that reason, they are dihedral mirror planes. All right, then let us just move from here to the next kind of symmetry operation, which is the inversion operation. So the inversion operation is abbreviated with the Schoenfeld symbol I, and each inversion operation is associated with an inversion center, also called center of symmetry, as the symmetry element. So in this case, we have a point as a symmetry element. So the inversion operation has the property that it converts any coordinates within the object x, y, z into the coordinates minus y, minus x, minus y, minus z. So we move every point of the object through the inversion center to the other side. So for instance, you see here an octahedral molecule, which is an SF4 molecule in this case. So it has, 6 fluorine atoms surrounding the sulfur atom in the center, which are labeled here. So as we carry out the inversion operation around an inversion center, which sits here in the center of the molecule, then we'll move all the atoms through that inversion center to the other side. Okay, so the atom 1 will be moved to the inversion center into this position. So now it's here. The atom 2 will be moved to the inversion center to the other side. Now it's in this position. This atom 3 will be moved to the inversion center to the other side. Now it's in this position. The atom 4 will be moved to the inversion center to the other side. Now it's in this position. Atom 5 will be moved to the inversion center to the other side. Now it's in this position. And the atom 6 will be moved to the inversion center to the other side. And now it's in this position. Okay. So now, how many inversion operations are associated with an inversion center? It's only one, and that is because when we carry out the operation n times, and n is equal, when n is even, for instance 2, 4, 6, 8, and so forth, then we are always producing the identity. And when n is odd, so 1 equal to 1, 3, 5, 7, and so forth, then that's always as though we would reflect only one time. Okay? So, last but not least, we have the so-called rotation reflection operation to consider, and that's the most complicated operation because the operation requires two steps. First, a rotation around what is called so-called improper rotational axis, and then a subsequent reflection. So the rotation reflection is denoted by the Symmetry symbol S subscript n, whereby n tells you about the order of the improper rotational axis. So it's important to understand that only after both parts of movements, the rotation and the reflection, is carrying out, the operation is complete. Okay, so now let us do this by an example. So for instance, the methane molecule, and you see here the hydrogen atoms labeled 1, 2, 3, 4, has an S4 improper rotational axis. And that means now that we have to rotate around 90 degrees first, and then we have to reflect at our mirror plane that stands perpendicular to the axis around which we have rotated. So you see the improper rotational axis here, and you see that the improper rotational axis bisects the hydrogen bond angle here, and this hydrogen-carbon bond angle here. It goes through the two opposite edges of the tetrahedron. So the associated mirror plane stands here perpendicular to the principal axis. So now let us carry out the symmetry operation and see how the object moves. Okay, so first let us do just the 90-degree rotation, and we do the 90-degree rotation always counterclockwise. So regardless whether we rotate around a proper rotational axis or an improper rotational axis, by definition, we always rotate counterclockwise. Okay, so let's do this. And what happens then is that hydrogen atom 1 moves here from the paper plane to the back of the paper plane. So now atom 2 rotates to the front. You see it now here. So atom 4 is now pointing to the back, and atom 3 is now pointing up. So now you see that the object that we have created does not superimpose the original object. If I move this object over here, it would not superimpose the object. And that means that a proper rotational axis is not present, and just a rotation around 90 degrees is insufficient. So we now need the reflection in addition in order to make the symmetry operation complete. So we must now mirror here. So what is the result? Well, atom 1 will move through that mirror plane to the other side. Okay, and now it's here. Atom 2 will move to the mirror plane to the other side, now being in this position. Atom 3 will move through the mirror plane to the other side, now being in this position. And atom 4 will move through that mirror plane to the other side. Okay, now being in this position. So now we see that the object that we have created here can be superimposed with the original object. Therefore, our symmetry operation is complete and valid. Okay? So now the rotation reflection operation has also a number of properties. So one property is that the S1 symmetry operation is always identical to a conventional reflection. This is because when the order is 1, then that means that we rotate around an angle of 360 degrees, and that is as though we would not rotate at all. So in sum, we actually only reflect, and that's the same as what a regular mirror plane does. So now S2 is the same as carrying out an inversion. That is actually illustrated here. So when we invert our SF6 molecule, as we have seen before, then we produce this molecule here, in which basically the positions of fluorine 1 and 2 are being swapped up, 4 and 6 are being swapped up, and 3 and 5 are being swapped up. So now, when we carry out an S2 symmetry operation, we first have to rotate by 180 degrees. So let us rotate around an improper rotational axis that stands here, going through the atoms 1 and 2. Then atoms 1 and 2, they do not change their position, but all the other 4 atoms rotate by 100 degrees counterclockwise. So that means that atoms 6 and 4 swap up the position. 6 rotates here, and 4 rotates over there. And atoms 3 and 5 swap up their position. So 3 is rotated over here, and 5 is rotated over there. All right. So now you see that it's still not the same as just the inversion, but now if we are carrying out the second step, the reflection perpendicular to where we rotated, then this is the same as just an inversion. Because if we reflect here now, well, in this plane, well, the atoms 3, 4, 5, and 6 do not move because they contain the plane, but the atoms 1 and 2 are getting swapped up. Okay? So 2 moves over here, and 1 moves over there. And now we see that the two processes are identical, and that the S2 is the same as the inversion. So that means that actually we would not need the inversion, and we would not need the regular reflection as symmetry elements and symmetry operations. We could express everything by a rotation reflection operation. However, if we can, we use sigma instead of S1 and I instead of S2, simply because for the human mind it's easier to perform a one-step symmetry operation rather than a two-step symmetry operation. So it's just easier for us, even though strictly we would not need sigma and I. Okay, so that's one interesting property of the rotation reflection operation. So another one is that when n is even, then that molecule also needs to contain a proper rotational axis of half the order. Then in this case, when we rotate n times and reflect an equal number of times, then we produce the identity. However, when n is an odd number, for example, 3, 5, 7, and so on, then the molecule must contain also a proper rotational axis of the same order, and it must also contain a horizontal mirror plane. So now in this case, when we rotate n times, then we only produce, well, a molecule which is identical to a molecule that we would have produced through a reflection at a horizontal mirror plane. We need to carry out the symmetry operation 2n times to produce the identity. So for instance, if n is equal to 3, we would need to rotate reflect 6 times. If n was equal to 5, we would need to rotate reflect 10 times. Okay, so let us do this by one example, and I think we still have time for that. So here is the example of a PF5 molecule, which has a trigonal bipyramidal shape. So we have here an S3 improper rotational axis, and the mirror plane stands perpendicular to that. And now, as we carry out the symmetry operation, first rotate, okay, and then we reflect, okay. So now we have to do this well, 6 times, because the order of our improper rotational axis is odd, 3 in this case. So let us just prove that. So here you have again the PF5 molecule, and your fluorine molecules are labeled 1, 2, 3, 4, 5. So carrying out the symmetry operation just one time will swap up the positions of these two, and will rotate all the atoms in the equatorial plane by 120 degrees counterclockwise. Okay, so F5 will move from here to here, F4 will move from here to over there, and F3 will move from here to over there. So now, if we do this 2 times, well, then again, F1 and F2 are being swapped up, and the equatorial atoms, they rotate by 120 degrees counterclockwise. Now F3 is here, F4 is here, and F5 is here. Okay? So now if we do this 3 times, okay, then again F1 and F2 swap up their position. See here and here. And again, these 3 fluorines, they rotate counterclockwise. So F3 moves here, okay, F4 moves here, and F5 moves over there. So this actually, so F5 moves over here. All right. So now you see that this is the same as just reflect the horizontal mirror plane. As we go directly from here to here, we see that F5 is in its correct position, F3 is in the same position, F4 is in the same position, but F1 and F2 are being swapped up. Okay, so it's the same as carrying out a sigma H. So we must further rotate reflect in order to go back to our original molecule. So now if I do it 4 times, okay, again, F2 and F1 are being swapped up. These equatorial atoms, they rotate counterclockwise. So now F3 is here, F4 is over here, and F5 is over there. So now if we do it another time, then we again swap up F1 of F2. So F2 is over here, so F1 again is over here, F2 is over there. Now we have F3 in this position, and F5 in this position, and F4 in this position. So if we do it another time, then again F1 and F2 swap up, and these 3 rotate again, and then we have actually produced our original molecule. So how many S3 unique symmetry operations do we have thus far? So S36 is the same as the identity, and S33 is the same as sigma H. Now, S32 is actually the same as C32, and that is because if you rotate, if you reflect twice, then that's the same as not reflecting at all. So therefore, S32 is C32. And in addition to that, in S34, the same as a C31, because if you rotate 4 times, that's the same as though we would rotate only 1 time. And reflecting 4 times is as though we are not reflecting at all, because we're reflecting an even number of times. Okay? And that means that actually only the S31 and the S35 are unique symmetry operations. The other ones can be expressed by simpler symmetry operations. So let us stop at this point. Stop the